Around 2 in the afternoon, Cuba daylight time, a magnitude 6.1 earthquake broke beneath the waters west-northwest of Mantua, Cuba, and sent shaking far beyond western Cuba itself. Why does a quake of this size appear in a part of the Caribbean that many people do not think of as especially seismic? Why did one offshore rupture reach Havana, Florida, and Mexico's Yucatán Peninsula in a single afternoon? The answers sit in the structure of the region, in the old faults buried beneath the seabed, and in the long memory of Cuba's crust, which has been carrying tectonic stress for millions of years. The quake was located about 104 kilometers, roughly 65 miles, west-northwest of Mantua, and was initially reported at a shallow to intermediate depth of about 26 kilometers, 16 miles. The mechanism was reverse faulting, meaning the crust on one side of the fault was pushed up and over the other side under compression rather than sliding sideways in a simple strike-slip motion. No tsunami warning followed the event, and early reports from major news organizations indicated no immediate casualties or major damage. In other words, this was a strong and unusual earthquake, but not a catastrophic one, at least in the first public accounting. The shaking did not stay confined to western Cuba. It was felt in Havana, where buildings swayed enough to draw attention across the capital, and it was also reported in Florida, including South Florida and areas farther north, as well as in Mexico's Yucatán Peninsula, where Cancún, Playa del Carmen, and Tulum were among the places that noticed the tremor. That reach matters because it shows how efficiently seismic waves can travel through a broad region when the source is strong, shallow, and offshore. In places that rarely feel earthquakes, even moderate shaking can prompt pauses, evacuations, and a quick reassessment of what is happening beneath the sea. The event stands out because of how rare it is for a quake of this size to strike this part of the Gulf Basin. Reuters reported that it was the strongest earthquake within about 322 kilometers, 200 miles, of the epicenter since the 1880 San Cristobal event, while AP described it as the largest earthquake ever recorded in the Gulf region with modern instruments. Those are strong statements, and together they place the June 8 shock in a narrow historical class. It was not just another offshore tremor. It was a benchmark event for a part of the Caribbean margin that has long seemed quieter than more famous seismic belts elsewhere. Yet the word quiet can be misleading. The earthquake occurred within the North American plate, not directly on a plate boundary, and that is part of what made it unusual. USGS describes the Caribbean region as a place where numerous tectonic plates meet, interact, and deform one another, with active subduction, transform motion, and complex fault systems all overlapping in a relatively compact area. The quake west of Cuba was therefore not a random event in empty crust. It was a release of stress inside a plate that has been carrying the imprint of much older collisions and fault movements for a very long time. That distinction matters because intraplate earthquakes behave differently from the better-known earthquakes that occur right along active boundaries. The interior of a plate is generally less shaken, but it is not mechanically dead. Old structures can remain weak long after the tectonic episode that formed them has passed. When those structures are reactivated, they can produce earthquakes far from the nearest active boundary. That is the setting here. Western Cuba sits under a tectonic roof that was assembled during collision, compressed again, and later cut by fault systems that never fully stopped accommodating motion. The earthquake was therefore less an isolated surprise than a reminder that old crust can still move when the stress field lines up just right. Cuba's geology gives that idea depth. Geological summaries of the island describe a history shaped by collision between the Greater Antilles Arc and the North American margin, by the emplacement of ophiolites, by fold and thrust belts, and by later transform motion that reworked the same territory from another angle. In simpler terms, western and central Cuba are not flat, stable blocks of rock. They are stitched from remnants of oceanic crust, island arc material, and deformed sedimentary belts that were pushed, stacked, and welded together through a long tectonic campaign. The land and the shelf around it preserve that history in stone, and the reverse faulting earthquake fits naturally into a region built by compression. USGS notes that the Caribbean margin is geologically complex, with subduction and interacting plates affecting Puerto Rico, the Virgin Islands, and broader parts of the region. That wider tectonic framework helps explain why Cuba can experience both the legacy of boundary motion and the occasional release of stress inside the plate itself. The quake off western Cuba did not happen in isolation from the regional system. It happened because the region is a stitched boundary zone whose pieces have been moving in different directions over geologic time. The North American plate, the Caribbean plate, and older inherited structures all leave their fingerprints there. What looks calm on a map may still conceal a living fault architecture below the seafloor. The geology of western Cuba is especially important because it records one of the Caribbean's major tectonic transitions. Research on Cuba's plate history describes how the east-west striking orient-to-transform system became the northern boundary of the Caribbean plate during the Middle Eocene, while other work on the island's overall geology emphasizes the collisional stacking that followed earlier subduction and arc growth. That means the region's modern seismicity is not built on a blank canvas. It is built on a pre-existing fault and fold framework that has been inherited, buried, reactivated, and reloaded many times. The reverse faulting mechanism reported for this earthquake is consistent with a crust that has been shortened and compressed before, then asked to do it again. That is why western Cuba can feel like a geological archive. The rocks there do not simply sit in place, they record the collision of oceanic and continental fragments, the emplacement of ophiolites, the rise and collapse of arcs, and the later translation of blocks along strike-slip systems. The result is a region where compression, shear, and inherited weakness all coexist. A reverse earthquake in that setting is not a random anomaly. It is a mechanical expression of the same long tectonic story written in the island's mountain belts and offshore faults. The sea may appear still, but the crust beneath it has been arranged by forces that never fully vanished. The historical comparison makes the present event sharper. Reuters reported that the June 8 quake was the strongest within roughly 322 kilometers of its epicenter since 1880, when an earlier earthquake near San Cristobal was felt in Florida and caused damage and fatalities in Cuba, according to the historical context cited in the reporting. That means the region's modern instrument record has now captured an event that sits very close to the top of the local seismic chart. For residents and officials, the important point is not only that this quake was strong, but that the area has a serious historical precedent for damaging offshore or nearshore shaking. The human response reflected that rarity. In Cuba, strong shaking drew attention quickly because many buildings and utilities have limited resilience to a serious seismic event. Reports from international outlets said no immediate major damage or deaths were confirmed early on, but the concern was still real because the island's infrastructure has endured years of strain. In Florida, where earthquakes are uncommon, people described enough shaking to notice swaying, rattling, and temporary disruption. In Mexico's resort corridor, evacuations and precautionary protocols followed the tremor. That sequence is important. A single earthquake can become a regional event when it crosses political borders and catches multiple populations off guard at once. The physics of reverse faulting helps explain why the quake registered so widely. A compressional earthquake of this kind can transfer energy efficiently through the crust, especially when it is shallow enough to couple strongly with the overlying rock layers and nearby sedimentary basins. The reported depth, around 26 kilometers, 16 miles, places it in a range where the rupture can still produce strong surface shaking, even if it does not reach the surface. USGS's basic fault definitions note that reverse faults involve one block moving up over another under compression, which is exactly the kind of motion expected when a stressed crustal block releases stored strain. In an offshore setting, that motion can be felt far beyond the epicenter. It is also worth separating the event from the more familiar seismic geography of the Caribbean. Many people associate the region's strongest earthquakes with active plate boundaries farther east, or with the transform systems that run through other islands. Western Cuba is different. It sits near a broader plate boundary system, but the quake itself occurred within the North American plate, away from the nearest active boundary by hundreds of kilometers. That makes the event notable not because it contradicts Caribbean tectonics, but because it shows how old compression zones and transformed crust can still generate significant seismic energy without a direct boundary rupture at the epicenter. The broader Cuban landmass reinforces that lesson. Geological syntheses of the island describe a mosaic of continental platform rocks, volcanic arc remnants, oceanic fragments, and thrust sheets that were assembled over a long interval from the late Cretaceous through the Eocene and beyond. That kind of structure does not disappear once the main tectonic phase ends. It remains available for later reactivation. So when a reverse fault earthquake occurs west of Mantua, the event is not simply a dot on a map. It is a reawakening of a tectonic memory already encoded in the island's crust and shelf. In that sense, the quake belongs to the same geological lineage as the rocks beneath Cuba's western mountains and offshore basins. The absence of a tsunami warning also matters. Offshore earthquakes do not automatically produce tsunamis, even when they are strong. The key ingredients are the amount of vertical seafloor displacement, the size of the rupture, and the geometry of the fault. In this case, early official reporting indicated no tsunami threat, which suggests that the rupture did not generate the kind of seafloor movement needed to organize a dangerous wave train across the basin. That outcome does not reduce the significance of the earthquake itself, but it does narrow the immediate hazard footprint. Strong shaking was the principal danger, not a wave field racing toward the coast. The time of day also shaped how the event was experienced. Around mid-afternoon in Cuba, people were awake, active, and more likely to notice a sudden vibration in buildings, roads, and suspended fixtures. That helped spread reports quickly through social media, transportation systems, and news channels. In a region where many residents are not conditioned to expect earthquakes, a midday offshore shock can create immediate recognition that something unusual has happened. The event therefore became more than a seismological data point. It became a shared regional moment, felt in homes, offices, hotels, and transit corridors across the Western Caribbean rim. For Cuba, the event is a warning without being a disaster. It shows that the island's western flank can still produce strong shaking from an offshore source, and it confirms that the surrounding seabed contains faults capable of reverse motion. It also highlights a practical issue. When an earthquake of this size occurs in a region with older buildings, patchy infrastructure, and cross-border exposure, the first hours are about verification, communication, and structural checks. Even when the damage report is limited, the tectonic message is not. The crust offshore western Cuba is active enough to produce a significant earthquake in the modern record, and that fact will now sit beside the island's much older seismic history. The larger meaning of the quake is geological as much as practical. Western Cuba is not merely an island edge looking out over water. It is a compressed margin built from collision, thrusting, transform motion, and inherited fault lines that still retain strength. The recent reverse faulting earthquake exposed that architecture for a moment. The way a bright cut in a dark rock face reveals layers that usually stay hidden. It was a strong quake, a rare one, and a regional one. It was also exactly the kind of event the tectonic setting has been capable of producing all along. In that respect, the earthquake off Mantua was less a surprise than a reminder from the crust itself. Across the wider Gulf of America region, the earthquake also renewed attention to a question that emerges whenever a significant offshore event is felt across multiple coastlines. If shaking from a single rupture west-northwest of Cuba can be noticed in Florida and across portions of Mexico's Yucatán Peninsula, what does that reveal about the broader hazard landscape surrounding the Gulf Basin? The answer begins with geography. Unlike mountain belts that concentrate populations along narrow corridors, the Gulf of America is bordered by extensive coastlines containing major cities, ports, industrial facilities, tourism centers, energy infrastructure, and transportation networks. A seismic event occurring near the center or southeastern portion of this basin can affect communities separated by hundreds of kilometers and multiple national boundaries. The June 8 earthquake demonstrated that reality. Although the rupture occurred offshore of western Cuba, reports of shaking extended well beyond the island itself, reaching portions of southern Florida and eastern Mexico. For Florida, the event served as a reminder that low seismicity does not mean zero seismic exposure. The state is often associated with hurricanes, coastal flooding, and severe thunderstorms rather than earthquakes. Yet seismic waves do not recognize political borders or hazard reputations. Florida's geological foundation differs significantly from that of more earthquake-prone regions of North America. Much of the state rests upon thick carbonate platforms composed largely of limestone and related sedimentary rocks. While Florida rarely experiences locally generated damaging earthquakes, it can feel earthquakes originating hundreds or even thousands of kilometers away. One reason is that seismic energy can travel efficiently through portions of the eastern North American crust. Compared with tectonically active western regions where fractured rock can dissipate energy more rapidly, some eastern geological structures allow earthquake waves to remain detectable over greater distances. As a result, residents in Florida occasionally report shaking from earthquakes originating far outside the state. The June 8 earthquake reinforced that pattern. Although the epicenter was located offshore near Cuba, shaking reports extended northward across the Florida Peninsula. In practical terms, this means that future earthquakes occurring within the Gulf Basin, particularly larger ones, could potentially be felt across substantial portions of the southeastern United States. That does not mean Florida faces an imminent earthquake crisis. The distinction is important. Feeling an earthquake and suffering significant damage are very different outcomes. Nevertheless, the event highlighted the reality that offshore seismic sources around Cuba, the Caribbean margin, and the Gulf region remain capable of producing noticeable effects across the state. Mexico faces a somewhat different situation. The Yucatán Peninsula is generally viewed as one of the more stable portions of the country compared with the Pacific coast, where major earthquakes occur regularly along active plate boundaries. The peninsula lacks the dramatic mountain-building tectonics that characterize western Mexico. Yet the June 8 earthquake demonstrated that seismic waves from offshore Caribbean and Gulf sources can still reach the region. Cities such as Cancun, Playa del Carmen, Cozumel, and Tulum represent major population and tourism centers. Millions of visitors pass through these areas annually. Even moderate shaking can trigger evacuations, precautionary inspections, transportation interruptions, and temporary concern among residents and tourists unfamiliar with earthquake procedures. The geological character of the Yucatan Peninsula introduces additional considerations. Much of the region is underlain by limestone formations marked by caves, sinkholes, and extensive underground drainage systems. While these features are famous for creating the peninsula's remarkable cenotes and subterranean waterways, they also illustrate that the subsurface environment is complex. Ground conditions can influence the way seismic waves are experienced at the surface. In some circumstances, local geology can amplify shaking relative to surrounding areas. The June 8 earthquake was not large enough to generate widespread structural impacts across Mexico's Caribbean coast, yet it provided a valuable demonstration of connectivity within the Gulf Basin. A rupture occurring hundreds of kilometers away still attracted attention across major resort areas and urban centers. Looking at the broader historical record, the rarity of the earthquake may actually be part of the concern. Regions that experience frequent earthquakes often develop stronger public awareness, emergency procedures, and institutional familiarity with seismic hazards. Areas where earthquakes occur only occasionally may lack that same level of preparedness, simply because the threat does not occupy daily attention. That reality applies to portions of both Florida and the Yucatan Peninsula. When earthquakes are uncommon, residents may not immediately recognize shaking. Building managers may have limited experience implementing earthquake-related procedures. Public expectations are often shaped by more familiar hazards. Another factor involves the possibility of future events. Earthquakes do not necessarily occur as isolated incidents. Aftershocks frequently follow significant ruptures, and complex fault systems can continue adjusting after the initial release of stress. Most aftershocks are smaller than the main event, but they help scientists understand the geometry and behavior of the fault zone involved. Whether future activity remains limited or develops into a more extensive sequence, the June 8 earthquake has already established an important benchmark. It represents the largest instrumentally recorded earthquake within the Gulf region since modern monitoring began, and joins a very short list of significant seismic events documented in the basin since the mid-20th century. For Florida, the lesson is that distance alone does not eliminate earthquake exposure. For Mexico's Caribbean coast, the lesson is that stability does not equal immunity. For Cuba, positioned closest to the source, the earthquake reaffirmed the continuing tectonic activity hidden beneath surrounding waters. The Gulf of America often appears calm on maps, framed by coastlines better known for tourism, shipping, fisheries, and energy production than for earthquakes. Yet the June 8 rupture revealed another dimension of the region. Deep below the shipping lanes, coral reefs, and coastal cities lies an older tectonic framework shaped by compression, collision, and faulting over immense spans of geological time. Most days, that framework remains silent. On June 8, it spoke with a magnitude 6.1 earthquake powerful enough to be felt across 3 nations, reminding the entire Gulf Basin that even rare seismic sources deserve attention.